Yes, 31st lecture on BJT power amplifiers. Before we do power amplifiers, we'd like to work out at least one example on BJT biasing. While we design power amplifiers, we shall do further examples of BJT biasing, but one only BJT biasing. Let's take a BJT in which this is specified as 2K. RE is specified as 2K, so we don't have to assume a VE, and the collector current is specified as 1.25 milliampere. R sub C is not known. The VCC is specified as 15 volt, and you will now have to find out the other resistances, namely R1 and R2. VCE is specified as 5 volt. VCE is specified as 5 volt. Beta nominal is specified as 100, and beta minimum is specified as 70. You have to design the bias circuit. That's the question. So the Q point has been specified. The Q point is 5 volt, 1.25 milliampere, and you know where I sub B shall be. All you have to do is 1.25 milliampere divided by the nominal beta, that means 100. Alright. So you know what the Q point is. How do you establish this Q point? What value of RC do you choose, and what values of R1 and R2? That is the question. This is the total exercise. Now obviously R sub C, you see, if this is 1.25 milliampere, then what is this current? 1.25 plus 0.0125. So approximately 1.26 milliampere. And therefore R sub C shall be equal to 15 minus 5, then 15 minus 5 minus 2 times 1.26, so 2.52 divided by 1.25, so many kilo. Yes. Oh, this current is 1.25 plus the base current, and the base current is I sub C divided by 100. That's what I added here, 1.25 and 0.0125. Is that clear? This is 1.2625. I took it at 1.26. And you can see that this is approximately 6K. Alright. R sub C is known. What do you do next? You choose an R sub B. R sub B. R sub B should be beta mean, which is 70, 14K. Beta mean multiplied by RE, which is 2K, divided by 7, which is equal to 14K. No, I have made a mistake. It is correct. All right. Then we have to find out VBB. VBB would be 15 R1 divided by R1 plus R2. Well, this is R1 R2 divided by R1 plus R2. Alright, R sub B. Then this would be equal to, this is VBB, would be equal to IB RB, which is 0.0125 multiplied by RB is already taken, 14 times 10 to the 3. No, I beg your pardon. Don't allow me to make a mistake. Will this 10 to the power 3 be there? No, because 0.0125 is in milliamperes. Okay. Plus VBE, you take that as 0.7, plus VE. What is VE? 2.52 volt or millivolt? Volt. Okay, so you know what is R1 divided by R1 plus R2. Alright, from this equation you know what is R1 divided by R1 plus R2, and you know R1 R2 divided by R1 plus R2 as 14K. So all you have to do is divide one by the other, then you get the value of R2, and if you know R2 then you know R1, and the values are well, you find out the values. This is a typical design example, design for BJT biasing. We shall do further examples while we make actual amplifier designs, either power amplifier or voltage amplifier. And this is a point where we plan to start our discussion on power amplifier. Well, the difference between power amplifier and other amplifiers is that in a power amplifier your aim is to get as much power as possible into the load, as much power as possible into the load, and the ideal situation would be that whatever power is drawn from the battery, VCC multiplied by I sub C, that is the power drawn from the battery? Not quite. A little bit of power is also drawn at the base, isn't that right? VBB multiplied by I sub B. Now the total power drawn from the battery is therefore VCC IC plus VBB IB. But you know IB is beta times less than I sub C. VBB is derived from VCC, therefore VBB is less than VCC. Am I making sense? Therefore, no? Okay. The total power drawn from the battery is VCC I sub C and VBB I sub B. You recall that the equivalent circuit is you have VBB RB and the current that is drawn is I sub B. Alright. This goes to the transistor, and the transistor is R sub C plus VCC. There may be an RE. This goes to ground, and this current is I sub C. There are two sources of power. One is VBB. What is VBB? It is derived from VCC. VBB is VCC R1 divided by R1 plus R2. Alright. So the total power that is drawn, DC power that is drawn from the sources is VCC times I sub C plus VBB times I sub B. But you know I sub B is IC divided by beta approximately, and VBB is less than VCC. This is what I was saying, and therefore this quantity is less than VCC IC over beta, and with a beta of approximately 100 you can ignore the second term. You can ignore the power that is dissipated in the base, power that is taken in the base circuit. So the total power taken from the battery is approximately, call this P sub C, approximately equal to VCC IC. Is the reason clear? That the power taken in the base circuit is much smaller than the power taken in the collector circuit, and therefore the power taken is VCC IC. Now this power, yes.
We have to Thevenin's equivalent.
Yes.
For that. So in Thevenin's equivalent, the power is not the same. If we have the Thevenin's equivalent,
The current is the same, I sub B.
yeah, when we take the Thevenin's equivalent, the
Yeah.
voltage and the current across the terminals is the same.
Correct.
But
So the current in the load is the same. And where is this current going from? It is going from the source VBB.
In the original circuit,
Yeah, we are not using superposition. We are not using superposition. We are using the same source but converted to a Thevenin equivalent. This shall be valid. If you calculate from the exact circuit, it will be the same result. This is a simpler way of doing things. Because, let me tell you, there's a good question that he has asked. What we are doing is, some current is coming through this and some current is going through this. Okay? So it is VCC multiplied by I sub C, and the total power drawn from the source is VCC I sub C plus I1. Isn't that right? That's the only thing that is drawn from the source. There is only one source, and it delivers current in two branches. This is R2, of course, alright. So the total power drawn from the source is VCC multiplied by the current drawn from the source, which is IC plus I1. Now you can show that VCC I1 is the same as VBB IB. It's a simple matter of analysis. A few minutes and you will be able to show this. So my calculation of power taken from the battery is approximately VCC IC, because this I1 is very small compared to I sub C. Alright, at least beta times smaller. Therefore, the total power drawn from the battery is VCC I sub C. Now what is our purpose in a power amplifier is that this power, if possible, I would like the total power to appear as signal power. If it's a stereo amplifier and I am taking power from the battery, I would like the total power to be converted to signal power, which is of course not possible. Why not possible? Because to establish the Q point, you require a voltage, a DC voltage between the collector and the emitter. VCE is a necessary evil if it is an evil. And if there exists a VCE through which a current I sub C passes, VCE times I sub C must be the power dissipated in the transistor. Okay, so what I was saying is the power that is taken from the battery, you would like so many wishes that you make, you would like this power, total power, to be converted to signal power into the load. But that doesn't happen. Why doesn't it happen? Because of necessity, there must be a voltage drop between the collector and the emitter to establish the Q point, and therefore the transistor must dissipate VCE multiplied by I sub C. Call this PD, power dissipated in the transistor. Then you want that at least the rest of it, that is from VCC IC, VCIC is the power necessarily to be dropped, to be dissipated in the transistor. You want the rest of the power to be converted to signal power. Alright. So this is the purpose of a power amplifier, to transfer as much of DC power as possible to signal power. And in the process one makes compromises. Compromise is that you allow a little bit of distortion. Because the larger the swing of VCE is, the larger the swing of VCE, the larger will be the power transferred to the load. And to be able to get large power, you require large voltage swings and large current swings. And whenever there are large voltage swings and large current swings, you enter into the nonlinear region of the characteristics. And therefore you tolerate a certain amount of distortion. On the other hand, if it is a voltage amplifier, all that you want to do is to have a large voltage gain. And you will see later that voltage gain simply depends on the resistances. It does not allow the currents and voltages to have very large swings. It is not required for large voltage gain. Similarly, for large current gain, large swings of current or large swings of voltage are not required. What is current gain? Output current divided by input current. On the other hand, power gain of a transistor is not output power divided by input signal power. Do you understand this? The power or the efficiency of a transistor is that the input power from the signal will be very small. Sometimes you can feed a voltage without power. At the input of an op-amp, for example, op-amp does not take any power, right? But you require power at the output. So the power amplifier shall be characterized by signal power output divided by the power that is taken from the battery, and then you multiply by 100. This will give you the power efficiency of the amplifier. So the main point that I was impressing upon you is that in a power amplifier, the purpose or the objective is to transfer as much battery power into AC power or signal power as possible. On the other hand, this is not a requirement in a voltage amplifier or a current amplifier. And therefore our design of a power amplifier shall be governed by very different rules or very different considerations as compared to voltage amplifier or current amplifier. And one of the basic figures that one should understand is this, that in the design of a power amplifier, is this figure quite visible? Yes, okay. I'll go very slow on this. In the design of a power amplifier, the considerations are quite different from the design of voltage amplifier or current amplifier. And since most of you are familiar with power amplifiers, we thought we'd do power amplifiers first. Before we do, in what way? In turning your stereo into the full volume, and that is power. Okay? The considerations are the following. One is that the power dissipation. Every transistor, the manufacturer says you cannot dissipate more than 5 watts. Alright? So from a single transistor, you cannot dissipate more than 5 watts, and therefore the maximum power dissipation is fixed, which means that what is fixed is PD equal to VCE multiplied by I sub C. Alright? This is fixed. You cannot exceed this. If you exceed this, then you will burn the transistor. Alright? Now, obviously, in the VCE, in the I sub C versus VCE characteristic, what does this represent? The product is a constant, so this represents a hyperbola. Isn't that right? The product XY is a constant, this represents a hyperbola. And this green line that I show here is this hyperbola, the curve A. This represents VCE multiplied by I sub C equal to a constant. How to draw it? You take any VCE, let's say 20 volt, and find out the corresponding IC, which is PD divided by 20. Go to that point, and this is a point on the hyperbola. And similarly, you draw several points, then you draw this line. Alright, I have shown this as green, hatched area. This is the cool area, and that's why the color green, okay? Beyond it, I should have painted it red, burning, hot area. You cannot go beyond this, alright? So this is the ultimate constraint. This is the this is the fence beyond which you cannot go. Now there are other fences in this consideration, and one of them is the maximum voltage between the collector and the emitter. You know that if the collector base junction is reverse biased, and therefore if you go on increasing VCB, which also increases VCE, am I making sense? What is VCB? VCB is VCE minus VBE, and therefore if you increase VCE, VCB also increases, and you know that at a certain point avalanche multiplication or Zener effect shall take over, and this is why there is a slight tendency of these curves to go up. If you go beyond this, well, it will go like this. Agreed? And therefore there is a maximum VCE that is possible, and in this particular case the manufacturer specify that 30 volt is the maximum, and therefore there is a red fence here. You cannot go beyond this. Alright? So the maximum VCE sets the line B, a vertical line. You must not exceed VCE 30 volts. Alright? So this part is fixed. Then you cannot go to a negative base current. The minimum base current is 0. You cannot go to a negative base current. Why not? Because then the transistor does not conduct. Alright? Base current can only be positive. It's an NPN transistor. Base current can only be positive. And therefore the curve for IB equal to 0, this is the curve C. Alright? This determines another fence. You cannot make your base to conduct less than this current. And what is this current? How much is this current? Beta plus 1 ICBO. You cannot conduct less than this current. Okay, so this is one of the, and the fourth line the line D is this line, this is the saturation line. You cannot make a VCE less than this, because then it's a highly non-linear region. Alright, you cannot go beyond this. And another reason is that if VCE is so small, then the collector base junction refuses to remain in the reverse bias condition. It becomes forward biased. And this is why this is called the saturation region. Alright. The fifth line, fifth fence is determined by maximum I sub C, maximum collector current. Alright. Maximum collector current, obviously you cannot exceed a certain maximum, but usually the maximum collector current, you must understand this, it is not set by dissipation. It is not set by, you cannot increase voltage beyond 30 because avalanche multiplication takes place. You can increase the current beyond this, however, but the manufacturers, very clever people, they say we will specify your transistor that you are going to buy from us only within a certain maximum collector current, and this sets the maximum. This sets the line E as indicated here, and therefore you have a completely bounded region within which you must operate the transistor. The question now is this point clear? That is a completely bounded region? Okay. It's bounded by 1, 2, 3, 4 straight lines and a hyperbola. The hyperbola is the so-called power dissipation hyperbola. That is VCE times I sub C is a constant. The question now is, within this region, where should your Q point be? Where should the operating point be? Alright. And that, for that, I shall project another diagram. Is this okay? You see, our boundary is this. This one, who sets this? IB equal to 0. Who sets this maximum? VCE. Who sets this hyperbola? Power dissipation. Who sets this vertical? Maximum current. And who sets this? Saturation region. You notice that this is slightly tilted. Why? Because it changes. The collector current changes with VCE slightly. This is also slightly tilted. That's because the saturation region is also slightly tilted. Now, the point is, where should we choose the Q point? 3 possible Q points are shown here, Q1, Q2, Q3, and the corresponding load lines. What is a load line? Load line is a straight line satisfying the relation VCE equal to VCC minus I sub C times R sub C. If there is no resistance in the emitter lead. If there is resistance in the emitter lead, then it should be I sub C RC minus I sub C plus I sub B times RE. Is that clear? No. This is VCC, you have RC, the transistor, then you have RE. So VCE is equal to ICRC plus VCE plus IC plus IB times RE. Usually IB is very much small compared to I sub C, beta times less, and therefore this is approximately VCC minus I sub C RC plus RB. Alright? And therefore the load line shall be a straight line with a slope of minus RC plus RE. Thank you so much. Yes. RC plus RE. Therefore, the load line is a straight line on the VCE IC characteristic with a slope of minus 1 by RC plus RE. This is what we have called here RL2 or whatever it is, RL. This is the DC load on the transistor. The total load is RC plus RE. Actually and exactly it is not RC plus RE, but it is RC plus RE plus RE divided by beta. Isn't that clear? Because it is IC plus IB. Okay. Now, so this line, for example, has a slope, this line, the green line. The green line, you see, is well within this boundary. It's a safe operation. You can put your Q point here and then you can swing the current and voltage right from this point to this point. But that does not take account of the needs of a power amplifier. In a power amplifier, you require maximum possible swing in voltage as well as current. Alright? And you want the transistor to be driven to its limit. What does that mean? You see, the larger the swing, the larger will be the power dissipation in the transistor, but the power dissipation cannot exceed PD, and therefore any Q point on this hyperbola will make sure that the transistor is being driven to its limit. Alright, so Q1 is not a good Q point as far as power amplifier is concerned. Power amplifier, for a power amplifier, the Q point should preferably be on the power dissipation hyperbola. That means either Q2 or Q3 should be a proper choice. Let's look at Q2. Q2 makes the voltage swing from here to here. Alright? Q2 makes the voltage swing from here to here. So the voltage swing is restricted, but the current swing, it goes right from here to the maximum possible current that it can go. Alright? So Q2, is the point clear qualitatively? Q2 restricts the voltage swing, but makes the current swing as large as possible. On the other hand, if you look at Q3, you see Q3 does not make use of the maximum possible current swing, but it makes use of the maximum possible voltage swing. Alright? And therefore one has to make a compromise. Obviously you see that it is not possible to choose a point which makes use of largest current swing as well as voltage swing. But it can be shown analytically that any Q point between Q2 and Q3, any Q point between Q2 and Q3 approximately makes PD a constant. Does it have to be proved? Any Q point on this hyperbola shall make PD a constant. Alright? Any point on this hyperbola has PD equal to constant, but any Q point on this produces approximately the same output signal power. This is what is to be analytically proved. We shall not prove it. We will request you to accept this without question. Alright? That a Q point between Q2 and Q3. What is Q2? Q2 allows maximum possible current swing, restricts the voltage swing. Q3 allows maximum possible voltage swing. This is VCC, but restricts the current swing to VCC by RL. Alright? Now, any point between Q2 and Q3 gives almost the same power at the output. The question now is, which point is better between Q2 and Q3? To get an answer to that, we require the characteristics again. Is there any question on this figure? That between Q1, Q2 and Q3, first thing is Q2 and Q3 should be better choices. The next question that we have to decide is, should we allow a larger voltage swing or should we allow a larger current swing. And to get an answer to this question, please look at these characteristics. If we allow a large current swing, then we are coming near the saturation region where the curves are bent. Alright, we are entering into the nonlinear region. So are we when we come to maximum possible VCC. You see the curves are again bent, but they are approximately parallel to each other. Even if they rise in an avalanche fashion, they are approximately parallel to each other. And therefore, purely from qualitative inspection of the diagram, one prefers to have a larger voltage swing rather than a larger current swing. Alright, let's look at an example. Let's look at this example, okay? Now before we come to this example, let's look at this circuit once again. It's the same circuit that I have drawn. This is the usual circuit for a BJT. You have an R sub C, you have an RE, you have R1 and R2, except that in this figure, what is new in this figure? There are 3 capacitors. Well, what is the reason for these capacitors? This is the input current source. Input source is shown as a current source. It could be a voltage source also. But you know, because of source transformation, all that you have to do is to include a resistance here. Alright? Which can be combined with R1 if this capacitor was not there. Alright? But first thing first, let's look at these capacitors. Why are the capacitors used? Okay, the first thing is this capacitor. If it is not there, then VCC, this source shall see R2, R1 will be parallel by the transistor and also by the source if this capacitor was not there, and therefore unnecessarily some amount of power shall be wasted. We don't want the DC power to go into the AC source. For example, this could be a microphone or this could be from a transformer, and if this is a large DC, let's say 100 volt, then it might saturate the core of the transformer and the whole signal capability is lost. It could be an LVDT, linear variable transducer, okay, whose core may be saturated because of passing of DC. So DC must be blocked from this signal source. This could be a microphone, as I said. Alright, so there is a capacitor here. The purpose of this capacitor is to block DC, and therefore this capacitor must act as open at DC, but at the same time signal current should be able to pass to the transistor, and therefore the capacitor must be large enough to allow signal currents to pass. What does that mean? It means that its reactance 1 by omega C at the frequencies of interest should be small compared to the impedance that it faces. What is the impedance that it faces? R2 parallel R1 parallel the impedance that is presented at the input of the transistor. This is the purpose of this capacitor, and it is aptly called a coupling capacitor. It couples the AC source to the amplifier, alright, the transistor. In a similar manner, this capacitor is also called a coupling capacitor. The reason is that this couples the amplifier, the transistor, to the load. The load could be a speaker. You know, a speaker is an 8 ohm load, alright, 8 ohms, and your transistor BJT biasing may require 1K RC, alright. How do you get this? Therefore, what you do is, for biasing you use an RC, but for load you connect the load through a capacitor, alright. This capacitor, if the capacitor was not there, then the biasing would have been affected, because VCC would not only pass a current through the transistor but also through RL, and therefore this is also called a blocking capacitor. It blocks DC. Third capacitor, the capacitor across RE. Well, obviously this capacitor also is to be AC short, signal short, and DC open. All right. Now the third capacitor, okay, the third capacitor is inserted here for one reason. The reason is the following: the signal power, the signal voltage should appear from the collector, the base to ground. The signal voltage appears from the base to the ground. Part of the signal voltage is from base to emitter, and part of it is across RE. Is that clear? We don't want this. We want the total signal voltage to appear from the base to the emitter, because it is this signal that is amplified. The signal voltage that appears across RE provides what is called a negative feedback. That is, it effectively reduces the input signal to the transistor. All right, and therefore we don't want that. What we want is that RE should be AC short. That means, as far as signal is concerned, this point should be at the same potential as this point. On the other hand, we know RE. Why couldn't we do without RE? For biasing, for stabilizing I sub C, we do require an RE. Therefore, we have to put an RE, and we have to bypass RE for AC by a capacitor, and therefore this capacitor is called a bypass capacitor. It provides a short for AC. AC does not pass through RE, it passes through this capacitor. And since it is connected to the emitter terminal, it is called an emitter bypass capacitor. Is that okay? The three capacitors, do you understand this? Pardon me? Blocking capacitor is this one and this one. Okay, they block DC. But this is called a bypass capacitor. All right? Okay. Now you should understand, it also creates complication now. It creates complication. It's not as simple as we have presented here. Because, you see, for DC, the effective load is RC plus RE. For DC, VCE, as we said, is equal to VCC minus collector current multiplied by RC plus RE. On the other hand, for AC, RE is shorted. RE is shorted. So RE does not present a load. But RC, what is the AC potential of this point? A battery, internal resistance 0. So the AC potential should be 0. And AC potential of this point is also 0. Therefore, RC and RL are connected in parallel, because this is an AC short. Therefore, to AC, the effective load is not RC. The effective load is not RC plus RE. The effective load is RC parallel RL. Obviously, the AC load is smaller than the DC load, and it is the AC load which determines the amplification, not the DC load. You understand this? And therefore, there are two load lines now. One is the AC load line and the other is the DC load line. And let's look at this. Let's look at this now carefully. Look at this transistor characteristic. And please be with me when I explain this. This green line which starts from VCC and goes to VCC by RDC. What is RDC in our case? RC plus RE. This green line is the DC load line. And normally, if the DC load was equal to the AC load, then you would like to choose your operating point or the Q point approximately the middle point of this. Isn't that right? so that there are equal voltage swings on both sides and equal current swings on both sides. Okay. The AC load is not RC plus RE, but it is RC parallel RL, and AC load is smaller than the DC load. The slope of this line is minus 1 over the load resistance, and therefore the AC load line is tilted in the clockwise direction. Therefore, this orange line is the AC load line, and we have shown that the AC load line also hinges at the same operating point, Q point. Why is it so? The AC load line must also satisfy. That's correct. At this point, the input signal current is 0. This is the DC quiescent point. DC quiescent point is also the AC quiescent point. Alright. Therefore, once you settle on the DC Q point, the AC load line hinges on this point and goes slightly above. That is, it goes slightly in the clockwise direction. Alright. Now, when it does so, then obviously for power amplifier operation, you must restrict it between this point. You see, it doesn't go right up to the VCE axis. Why not? Why not? Because you cannot go below IB equal to 0. It must end here. Similarly, it cannot exceed this point, because then it will go into the non-linear region of the characteristic, and therefore your operation is restricted between this point and this point. This is the Q point, and your operation is restricted between this point and this point. There are slight distortions because you are driving the transistor to its limit. Whenever you drive anybody to one's limit, well, one cannot give the maximum, but it gives as much power as is needed. You pay a price. The price is slight distortion. Alright. It also shows what happens when the base current is allowed to fluctuate through the complete range. Okay. This is the base current sinusoid. The zero current is here, zero signal current, maximum signal current is here, minimum signal current is here. Alright. So the base goes through a complete fluctuation, complete cycle. The collector current similarly goes through one complete cycle. The collector current, as I had indicated on an earlier occasion, is in phase with the base current. When the base current is maximum, the collector current is also maximum. The corresponding variations in the collector to emitter voltage is this, and this is out of phase. Isn't that right? When the collector current increases, VCE decreases, and therefore there is a phase change between the base voltage or base current with the collector to emitter voltage. Alright. We will, alright, let's see. Is there any question? Then we will conclude with a simple example which can be answered by looking at the graph. The DC load line and AC load line for this example are the same, and it is this orange curve. The Q point is here at 7.5 volt DC and 5 milliampere. Can you tell me what is the maximum possible voltage swing? If this is 7.5, the DC load line and AC load line are the same. In other words, there is no capacitor taking pure load. It's RC. Well, 7.5 volt is the Q point and therefore approximately the swing is how much? 7.5 volt. That means it can go 15 here and approximately 0 on the other side. So 0 to 15. What about the current swing? 0 to 10 approximately. It would not be quite 10, it would be about 9.5 or so up to this. Alright. So can you tell me what the load line is? What the load resistance is? No, just a second. What is the load resistance from this graph? This is approximately 10. This is approximately 10 and this is 15.
Minus 1 by 1.
The resistance is 125. No? No. How much? This is 10 milliampere and this is 15 volt. So 15 divided by 10. 1.5K. Alright. We know this load. Then what is the peak value? What is the what is the power dissipation? Five times 7.5, which is 37.5. That is the maximum dissipation allowed in the transistor. Is that okay?
Yes, sir.
We cannot exceed that. Alright. And if the collector current is to swing from, let's say, 0 to 9.5 milliampere, which is approximately here, what is the corresponding base current swing? You see? These are things which have to be read from here. How much? This is obvious, it's given. 0 to 0.25 milliampere base current swing. What is the corresponding collector current, collector voltage variation, collector swing? It's slightly asymmetric. We can go right up to, you see, the zero base current is here. Zero base current is here. That means ICBO is approximately 0. So we can go right up to 15 here. But can we go right up to 0 here? No. Because the current is here. This is about 1 volt. This is 2.5. This is about 1 volt. So if the symmetry is to be maintained, but the swing will be asymmetrical. 7.5 to 15 and 1 to 7.5. And therefore your collector voltage swing is restricted to 6.5. That's right, peak value. These are practical considerations one obtains by looking at the graph. Alright? Whereas in the design one has to look at these carefully because these are realities of life and cannot be ignored. With this happy note, we conclude the class.